Hello everyone, welcome to lecture 6 of the Gyan lecture series. So, what I'll be talking about today is tomographic imaging. Okay, so I've discussed this a little bit earlier, like what does tomographic imaging mean? To recap, so if you want to find a three-dimensional structure of an object, then finding the three-dimensional structure is called tomography. And there are several different ways of doing tomography. And based on each one of these methods, there are different kinds of instruments people have built. That's essentially what we'll be discussing. In the lecture on X-ray CT and like I discussed some of the other imaging methods, I gave you a brief overview of how these methods work. Today I'll go into a lot more detail as engineering details of how exactly these things work. Okay, so the framework for today is you have an object in this shape. There is something in between inside it. You want to find the three-dimensional structure of that object. So what you do is you typically shine some light or some kind of radiation from this particular view, from this direction, and you make a measurement. You get an image of some sort. It could be a point measurement, an array measurement, like a line measurement. You get a measurement on the other side, and then you change the view and you get another measurement, change the view and get another measurement, so on and so forth. So basically, this is the general process for tomographic imaging. There are variations and there are nuances. There are different ways of doing it. That's actually what we'll talk about today. Okay, and the general way to think about this process is you have an input, which is the light that comes. Sound is okay. Yeah. And you make a measurement, and so for every view happens. So this for every view, light comes in. It goes through the system, which is the object and the instrument in this case, and you get data. Okay, so the data that you record is related to the object itself. F of R prime is basically the entire object. So different points in the object are R prime. So basically, for every single point here, there is a transfer function H of R and R prime. So for every point, this transfer function takes into account both the input and everything that goes on in the instrument, and it gives you the data. In other words, this equation here relates the data to the object, and H tells you the instrument properties and instrument parameters. And what we need to do is, from the measured data, go backwards and figure out f of r prime. The question is how to do that, and that's exactly what we'll discuss in the next, like in today's lecture. For different instruments, the approach is slightly different depending on exactly what happens inside the instrument, and that's what we will use. Okay. The first idea that I wanted to discuss was what's called ray tomography. So this is the principle, for example, X-ray tomography and X-ray CT, and some of these methods use an approach of this sort. There are several instruments, but I'm giving you some of the examples. And the basic idea here is you have an object, you think of the light as a ray. So we use ray optics. The ray picture of light is a good starting point for this type of analysis. And so array of light. Can you hear me on that? Okay. The array of light goes through the object, and so if you think of an infinitesimal element dl, so there is some amount of absorption. So at every point, depending on the absorbance property alpha r, Alpha is the absorbance at any given location. So at as the ray goes through, a small amount of light is absorbed, and it's proportional to delta L and alpha. So the how much of light is absorbed is alpha of r times dl in that infinitesimal element. And what you do is add up the contributions of how much absorption there is at all these points. So light comes in, a slightly smaller amount of light goes out, and it goes to the falls in the detector, and you make a measurement at the detector. So the how much light, so you know how much light is sent in. So how much light goes out depends on how much of it is absorbed. It's an integral. It's like little bit is absorbed at every location, and that's related proportional to the absorbance at that point. So you add up all these contributions. So in other words, adding up contributions is just adding small pieces. Integration is integration, right? So integrate along the line. It's a line integral through the object, and the light that comes out is e to the minus. So it's an exponential decay, right? In the previous class, we saw when you have absorption of light, it's a decaying exponential, and that decaying, this is exactly the decaying exponential, e to the minus of the absorbance, like absorbance times length, basically, and across through the entire ray, in line integral on the ray. So that forms your measured. So this is my measurement at one point. So for any one point, one ray goes through, and this is one pixel, one measurement that you make. So that's, and if you take the log, because you have an exponent here, you take the log on both sides, natural log, and you can get this kind of an equation. This is the relation. This is what happens in the instrument. And so you can do this for several different points. So you can, so instead of one ray, you can have multiple rays going, and you can parallelize the measurement for every one of the rays. You can get different measurements at different points. So you can have one source and one detector, or let's say 10 sources and 10 detectors, or any number of configurations. And if the light goes straight through, you can make separate measurements. This is at a certain angle, right? Certain view. The light is going through in a certain direction through this object. So with like V is the view, the angle, direction at which this light comes in. And so for different values of V, you make measurements, and this is the overall data that you collect after the entire imaging process. Questions so far? Okay. So the next thing is, how do we, like, where I'm going with this is, now that you get the data, how can we go from the data to the object itself? What is the structure inside the object? So how do we figure out the structure from the data, the measurements that you have made? The basic principle is that if you look at the object from multiple different points of view, that you can, so each like measurement is essentially like a projection onto the, so if you have a object, it has say two dots of the sort. You look at it from this point of view. Light goes like this, and you have like one peak here, like this, and another peak here, right? Corresponding to this. So, but if you look at it from, like say a different angle like this, then you will have basically like just one peak, because they will like one on top, there will be one on top of the other. But if you see it from a completely different angle, then you will have one peak here and another peak here. So depending on which angle you look at, you can get different kinds of data. And from all this data that you measure, so each measurement is a projection through the sample. projection meaning it's like we're compressing the sample and kind of measuring what's going through it. It's like in other words, it's like a shadow of the sample that you get. Each measurement is a shadow. You're taking multiple shadows and trying to figure out what is the inside, what is going on inside. Okay. So to give you an example of one example here, so you have like some three objects here. If light goes through and this is an array detector, so we are assuming that the sensor or the detector is an array. The source is also an array, and it's a bunch of parallel lines, and it covers the entire object. If this source makes a measurement with this sensor, and when you make a measurement, it looks something like this. So for example, here, this dot here corresponds to this peak here. This and this combined together will form this blob over here. So that's the projection. So this, I am saying this qualitatively. There is a more mathematically precise way of saying that. And here is, this is, yeah, so let me erase some of these things and show you a focus on this equation over here. So G of S is the measurement, whatever you measure on the detector. It depends on f of x comma y. So let's take the simplest case where the object is like this and the light is coming along the x-axis. So it's basically you're projecting on the x-axis. How do you project on the x-axis? It's equivalent to integrating, like projection is basically an integral, right? So therefore you have f of x comma y dx dy, but you're compressing along, so y equals like delta of y minus s. So what does that mean? Any value of y equals s. You like this g of s, g at any point s is basically the integral at y equal to s. So you're integrating along the x-axis, and that's how you get. So it's a so think of it this way: it's a two-dimensional function. You're integrating along one dimension, you get the other dimension out. So x comma y, you're integrating along x, you just get the y, and in this case y equal to x. Y is the same as s axis. So it's integral along the x-axis. For like if you integrate this object along the x-axis, that is the data you collect. Okay. So this is only a special case where it's light is exactly along the x-axis. What if it's not along the x-axis, but in more general situations? So one way to think about it is, instead of it being like this, instead of rotating the view, you can rotate the axis of coordinates and then do the same measurement, right? So you can rotate the axis of coordinates, and then this would be a projection along the y-axis, for example, right? So you can so here is an examples of these kind of projections. So you can project it along the x-axis, and here you can project it along this dimension, this y-axis here, project it along 45, is like 135, and so on. You can see exactly. So for example, here there is one dot here which gives the big peak here. This circle gives you this circle gives you this peak. So, and the overall absorption inside gives you the overall shape at the bottom. So basically this is how you can think about the set of measurements. Notice that this measurement looks a little bit different from this and different. So they look slightly different, and we will put together this data to give the overall final kind of output. Yeah, so the equation, so what is the equation for the data for at any given angle? What is the equation for the data you get? How do you kind of relate the object to the data you expect to measure? So the equation is as follows. Like, it looks long, but it's fairly simple. It's along the same lines as what we had before. Okay. So basically take the object fxfy, draw a line, this integrate along this line. So the delta function defines a line and you integrate along that line and you get the data. That's really all this is saying. And what kind of line is this? If you remember your 11th and 12th, what does the equation x cos theta plus y sine theta equals to p? Do you remember what this is? This is the parametric form of a line, right? If you have, let me draw it over here. So if you have a line like of this sort, then the equation, and if this is p, then at any point x comma y, and this is the angle theta over here, x cos theta plus y sine theta equal to p, right? And so this distance here is p. So what we are doing is taking this axis, let's say you are 0 here, so this distance is s. Now we are saying, let's use a different color, so x cos theta plus y sine theta minus p or minus s. If this is equal to 0, then it is this particular point, right? So you integrate along, if this defines like x cos theta minus plus y sin theta minus s equal to 0, defines this line. Okay, and so that's essentially what we have: x cos theta plus y sin theta minus s. So that one particular line, if you integrate on one of the lines, integrate the object along one of the lines, that is your data point g of s at an angle theta. For this particular angle theta, g theta of s is the projection along the in the direction theta. Okay, so theta is this angle here. You project, right, and you get your data. So for every angle, and so you can repeat this for different angles, and you get each time you get some data, and you record this data, and yeah, for any arbitrary direction. So in ray tomography, so this s equals x cos theta plus y sin theta. So this is basically, if you remember your coordinate geometry, if you have x and y, so you can have s and u. That's basically after, so you can rotate it. It's after you rotate your axis, the axis of coordinates, then basically you can get, like, this is the transformation from one axis of coordinates to another, right? So you can go from xy to su, or you can go from su to xy. So you, like, I'm sure most of you here know how to do this kind of coordinate geometry transformations. And therefore, if you take g of theta, you can also write it as f of, instead of in the previous case, x comma y, f of x comma y, you can write it as f of s cos. So let me go back to the previous slide. Look at this equation at the bottom over here. So all we are doing is basically looking at the x comma y, substituting for x and y, and like this delta function becomes like collapses, right? You can, like, after you rotate the coordinates, it's only integral along one direction, u. So you get x equals s cos theta minus u sin theta, and y equals s sin theta plus u cos theta. So you're integrating along, after rotation of coordinates, you integrate along one dimension. So you do a projection and you get the data. That's really what this equation is. Okay, and this in fact is also called the radon transform. There is an interesting history for this. So basically, um, when people were trying to invent X-ray CT, like a scientist by the name Paul was the pioneer in this approach. This was in the 1950s or 60s. So they were trying to figure out how to do this kind of 3D imaging. So he derived this independent, like sort of, he derived all this for X-ray CT. And later on, when he was reading the literature, like sort of after, in fact, after several years, people figured out that a scientist by the name, mathematician by the name Radon, actually had figured this out in the 1910s to early 1900s, and he had published it in a math book, some math somewhere, but nobody knew about it at that time. It was only rediscovered later. So kind of, so it was in some sense discovered by twice by two different people, and once by an engineer who was trying to make the instrument, and another mathematician before that. So this kind of so it basically going from these two dimensions and rotating the axis of coordinates and doing this projection is now called the radon transform. In short, you have the sample, it goes through the radon transform, and you get your data. So that's the way to kind of the simple way to read this. So also, if you another way to write it in shorthand notation, instead of writing this equation, you can write it in what is called an operator notation this way. The data here G is related to the object, and R is the radon transform, or the operation that connects the object to the data that you have collected. So this is the forward radon transform. So the question then is, how can, if you record the data, can you find F from G? So in other words, because we know R, there must be a way to you do some kind of inversion and get to the other side, right? Get F and remove the consequences of G. So this is a general principle in a lot of imaging systems, which is you have a sample and you want to find the properties of the sample. There is an instrument which does the measurement, and then you get data. So you know something about the instrument. You have to model the instrument in some way, and that is an operator acting on the object, and that gives you the data. And the process of figuring out doing the inversion, in other words, figuring out what the object is from the data is, you like model the instrument and basically do the inverse of what the instrument does, and that way you get the object. And the question is, is there an inverse for the radon transform? Yeah. Mm-hmm. Yes. Uh, that's why this exactly. So that's why it's a difficult problem, and that's why it took people a long time to figure out. Yes, what you said is absolutely right in the sense that if this was a simple kind of like algebraic equation, linear equation of the sort, that, so this is R is in some sense an operator. It is not like if it was simple multiplication of uh, like if G is a number and R is a number and F is a number, you could do 1 divided by R on the other side and get your answer, right? Essentially. But it's more, because it is more complicated, that's why you need a new method to solve the problem. Yeah. Uh, so R does not depend on the object itself. So is, like, are you talking about the object or? Are you talking about? Uh, mhm, mhm. So, if this R gets confusing, the simple, just look at this equation and maybe this will help, okay? For any given one angle theta, for all values of S, you can get theta. And then for a different value of theta, you can, for all values of S. So for like a pair of coordinates S and theta, for every S and every theta, you will get kind of, yes, different values. Completely different separate values for every pair of S and theta. Mhm. So yeah, so to give you a intuitive feel for what the data would look like, let's say you have the object is just one point, one dot somewhere inside the sample, right? So if you actually select the data, if actually let's call this the 0 degree angle. So if you project along this direction, there will be a peak here, and the rest of the data here, it's basically assume that it's minimal absorption here. So it is 0, and then the small peak at this location. And so if you look at the data, it looks something like this. If you start from some origin this way. If once you rotate it to 45 at 45 degrees, if you look at it, instead of it being on the right side, it will be in the middle, right? The data, the will be in the middle. And then when you rotate it again, if you project it, it will be, in fact, if you look at the data from here to here, it will be slightly on the left side. And if you rotate it again, it will be even further to the left over here. So, so this is a function of s for one theta, function of s for another theta, function of s for another theta, and so on. So for different values of theta, you s and theta, you have this, right? So in the xy coordinate space, the object is at one point. That xy coordinate space here, the object is at one point. But in the s theta coordinate space, right? In this case, I'm plotting the s on this axis and theta. But at any given angle, if you make a look at where the value is, right? If you make a plot of that sort, it looks something like this. It's called a sinogram. It will have like a sine like shape. And so basically this is the, so a point in the xy space becomes a trace, a line, like a line of a specific shape in the what is called the s theta space. Okay, so this is intuitively, this is the nature of the data you expect from ray tomography. And this kind of a curve is called a sinogram. Now, if instead of one dot, if you have multiple dots, if you have three dots, for example, each of these dots will have its own sinograms as curves that traces in this S theta space, and therefore you get curves of this sort. If the data you actually measure, if you put them on on a two-dimensional grid of S and theta, it will be something of this sort. And the question is, can we use this and get to this somehow? Okay, that's the next question we will answer. Any questions before that? Okay. So the solution to this problem is what's called the projection slice theorem. Okay, the theorem essentially is as follows. So let's say we have we take the object at and look at it at an view it from an angle theta from the vertical. Then if you make this projection gs of theta, what you do is take gs of theta, take the Fourier transform of gs of theta. Okay, good. So the 1D Fourier transform of for along s is the variable, theta is the parameter, and so take the Fourier transform with respect to s. Then you get, for that theta, you get theta of Ks. So the Ks is the Fourier variable that we are using, and so take the Fourier transform of that. The projection slice theorem says that that is equivalent to the slice of the object along this direction. So let's say the object has so fx fy is the object. Take a so fx fy f of x comma y is the object. Take the Fourier transform of the object. So in the Fourier domain, in the two-dimensional Fourier domain, so where you have kx and ky axes, there is some kind of, it will have some values, right? So now projection along this direction is equivalent to taking a slice of the Fourier domain at an angle theta to the x-axis. So this is called the projection slice theorem. Projection along one domain is equivalent to projection of the data is equivalent to taking the Fourier transform and then taking a slice in the Fourier transform at the angle theta. So this is the angle theta here. This is the angle theta at which you slice the Fourier transform. Okay. So this, yeah. So fxy, f of x comma y, if you take the Fourier transform, you will get f is confusing. This is the kx, ky. These are the Fourier axis, Fourier x-axis and Fourier y-axis of kx and ky. Okay. And so basically, this is So this allows us to. So now that you know this projection slice theorem, how can we figure out the object from the data? What do you think is the way to do it? Any guesses? You can guess it. I just want to see how you think and what you like. So I'm telling you that there is a theorem which says the data that you get, if you take the Fourier transform of the data, that is a slice in the Fourier domain. If you know this basic theorem, then how can you construct the 3D, this fx fy, the 2D object in this case, the slice, the cross section of the 3D object, so the fx fy, how can you figure it out? So what do you integrate? You're on the right track, you're close, but there is one small piece which is kind of missing, but you're almost there. Any other? You're very close. Anyone wants to also take a second guess? So what you can do is basically take the data, take the Fourier transform of the data, literally put it in the Fourier domain. Take another data at another angle, put it in the Fourier domain. Take the another angle, just populate the Fourier domain. Just think of it as a matrix. You are filling the matrix and fill the values of the matrix. And after you have filled it at all different angles, you have the full Fourier domain. You take the inverse Fourier transform and you get your answer. As in, there is a little bit more to that, but that's the basic idea. Do you populate the Fourier domain by the different Fourier transform of the different slices? And now that you know in the Fourier domain, you know the data. In the space domain, you do the inverse Fourier transform to get the answer. Okay, that's the essence of the idea. Okay, so you don't do any like integration or anything. You just literally put the data into the Fourier domain. That's the only subtle difference with from what you said. Okay, the only issue, like, does anyone see an issue with that? Do you see a kind of small problem that you will encounter when you actually try to do that? Yes, not yes. So basically there are gaps here, right? So you have very high dense sampling here, and as you go farther away, you have like gaps and like kind of farther, like there are kind of it gets more and more. So you are like getting like as you go away from the center, you're getting less and less data. So the middle you're getting a sampling a lot, farther away you're sampling less. So it's not uniform sampling. If it was uniform sampling along the kxky domain, then you can immediately take the inverse Fourier transform. But you're not doing a kind of populating it exactly at like uniformly spaced intervals. There is kind of like away from the center, you're like doing less and less of sampling, right? These regions here are sampled less than the regions close to the center. So that's kind of, you have to essentially correct for this particular problem. If you can correct for it and then take the inverse, that's your answer. Okay? So this data is a line, and the Fourier transform of like is basically therefore it's a line. This is one dimensional, right? So one dimension. This is one dimension data. One dimensional data. So you will put into two dimensions, and therefore it will be a line. Okay. So that's the essence. Like I'll go into the little bit more details of how to do this, but that's the basic picture. The idea here is that like you take the data, take the Fourier transform. It happens to be equivalent to the slicing of the Fourier domain. Literally put that data into the Fourier domain. After some reweighting, you take the inverse, and you will get back your object. Okay, that's where there are I'll show you the mathematical steps, but the big picture idea of what we are trying to do, if it's clear, then you can follow the math much more easily. So mathematically speaking, g of theta, the Fourier transform of the data, is equivalent to f of k cos theta, ks cos theta, ks sin theta. Okay, so that's equivalent to saying we're taking a slice in the so k cos theta, k sin theta is a point here, right? Or different for a constant theta, k cos theta, k sin theta are different points along that line, and that's exactly what this here. This is the Fourier or the projection slice theorem, also called the Fourier slice theorem. Of course, there are a few different names. Yeah. Mm-hmm. 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 Not quite. Think about it a little bit more, and you'll realize you can't do that. So this is fundamentally you're like sort of you will like even so we have done the rotation of coordinates, and it's uniform after you do the rotation as well. Like the pixels are equally spaced, but still it is always because it's an r theta to xy kind of a transformation. There is always going to be some kind of preferential kind of the middle is more weighted more heavily. Okay, you can think about it a little bit more, and you'll realize quickly that you can't get uniform from uniform xy to uniform r theta. You know the Jacobian of the transformation in integrals when you basically do xy to r theta transformations. There is a r d theta dr like kind of so the why is there an r because like That's the reason. That's the same reason why there is a weightage, heavy weighting to the. So you cannot avoid the. You can't do dr d theta. You can't do uniform sampling along r and uniform sampling along theta. It will not be the same as uniform sampling along x and uniform sampling along y. That transformation is not the right transformation. Okay. So yeah. So for like the simplest case, fairly easy to see how this projection size theorem works. So for example, if you have an object which is f of xy, you integrate along y-axis. So you compress it along the y-axis and to get like data along the x-axis. Then if you take the Fourier transform, let's say take like fxy. So if you take the Fourier transform at y equal to 0, right? Or ky equal to 0. So this is the equation fxy e to the j k x dx, right? So basically look at this equation. So now you have fxy and like you can like because e to the jkxx you integrate along dy, there is no y term here, so you can take this outside the integral and you can get like you can do a separation of variables in some way, and if you do this you get the data, like the projection data, which is basically your uh, Fourier transform of the data. I went through this a bit quickly. Let me slow down and perhaps let's explain this in much more, a little bit more detail. Okay. So this is this is your measurement. So taking the data and projecting, compressing it along the in the y direction to get like to get a function of x. You take the object, take the Fourier transform along the x-axis. So that is exactly this data over here. So this is so taking the Fourier transform along the x-axis, along the x-axis is equal. If you simplify the Fourier transform, you will end up with g of g0 of x, which is like projection of the data, projection of the object along the x-axis times e to the jkx, which is the Fourier transform of the data. In other words, the Fourier transform of the data is equivalent to the Fourier transform of the projection. Okay, so that's the Fourier size theorem. I've just proved this for the special case of one like projection along only the y, like integrating along the y-axis. But this is more general, and people have proved this for the more general case. I can go into the details, but maybe in the interest of time, I'll go ahead with this for now. Okay. So now the next question is, how do you do the reconstruction in the more general case? So this basic process of getting the data, like getting the object from the data, is called inversion by filtered back projection. So the word, so you're sorry with that. So back projection means that the process of measurement is equivalent to a projection. So you want to do a back projection to go back to where the data came from. That's the reason why we have the word back projection. Inverse means you're going, the process is going back in the reverse direction. So it's the inverse of the data measurement process. Filtered is because the weightage of it's not a simple kind of inverse. It is a weighted inverse. In other words, like the middle is weighted more heavily than the edges, and therefore you have to do some compensation, and the compensation is some kind of a filtering process. So what is a filter? It's some manipulation in the Fourier domain, and there is some manipulation in the Fourier domain that we will see it do and to get back the original object. Okay. So So FB is the filtered back projection. The data, the object you reconstruct after back projection, let's call it F of FB of X comma Y. That is equivalent to taking GS of theta, taking like, an integral of this. What is this? X cos theta plus Y sin theta minus S. What does, so if you integrate along this delta function, what do you get? What exactly is this? Exactly, yeah. So like, substitute S here. So using the sample, like sort of one of the properties of the delta function, you substitute S equals to X cos theta plus Y sin theta. In other words, you're integrating along a line, and that's like so if you integrate along the line, you get d theta of X cos theta plus Y sin theta d theta. Okay, so this process is going from the data to the object. This operation is that means denoted by the operator B. So this takes the data and tries to back project this project back to back projected to this. Okay, so the forward the measurement processes G equals R F. The reverse inverse processes FB equals B times G, which is B times R times F. So this is like, so if you can figure out B times R, then you can estimate like sort of if you make B times R equal to 1 through some process, then you will get back the original object, right? So that's the goal of inversion. So to represent, to give you a good feel for it graphically, so this is the previously what we saw, the different projections. So what we are doing in the back projection is taking this data, like figuring out where this comes from, taking the same data, back projecting it, putting it backward, kind of come to like through calculations, projecting it backward, projecting this backward, and wherever this kind of intersection meets, you are essentially you can figure out the value of this particular value of the absorbance of that object at that particular location. Okay. Yeah. So the process, so the connection between FB and F. So what is it that you like? So what is the why is so we have FB and we have F, right? So why? What is the connection? What is the similarity? What's the difference? What is the why is there a difference between the two? The reason why there is a difference is that the sampling of the object. So the middle of the object is much more sampled. So I showed you this picture here, right? So because you're undersampling the outer parts and oversampling the inner parts, you have to correct for this. And so therefore, when you simply do a back projection, it's not enough because you have to do a reweighting of these Fourier in the Fourier domain to account for the fact that there is heavy sampling in close to the center, and as you go away from the center, it's lesser sampling, and therefore that's exactly what we should do. So basically, FB of XY. So the back projected data is the original object convolved with some kind of a transfer function, and this transfer, like filter, happens to be 1 over rho. So this 1 over rho, as you can see, the small values of rho it's larger, and large values of rho it becomes inverse, right? So basically, and therefore in the Fourier domain, so this is a convolution in the spatial domain, it becomes the multiplication in the Fourier domain. So this is the filtering process that happens. Take a Fourier transform of this in 2 dimensions, it happens to be 1 over k rho. Okay, so basically take the data, divide by k rho. So k rho is like the Fourier variable in r theta coordinates in the Fourier domain. Okay, Do like multiply by this. So the back projected data is the original data multiplied by this 2 pi by 0 factor. So, and the factor looks like this. So this is the filter which you have to apply to the back projected data to get your original object. So that's why it's filtered back projection. So you back project and apply a filter, and that will allow you to reconstruct the complete object from the measurements. Okay. Yeah. So here is kind of yeah. So fb of x comma y is this. This is the back projection equation. So fb of x comma y, you write it as the g of theta. So instead of g of theta, you take the Fourier transform g of capital. So this integral in the square bracket is the same as g of theta. So you're applying the inverse Fourier transform equation, plugging it in here, and you substitute g theta equals to f of ks cos theta and my f comma ks and theta. Right. So this is the project from the projection side theorem. Substitute this into the projection side theorem. When you do that, what you have is basically fx comma y is before that. So fx comma y can be thought of as capital F kx ky. Let me capital F here. So is can be written as Fourier domain kx ky e to the j kx s plus ky y. So this is the definition of the inverse Fourier transform along two dimensions. So if you substitute kx equals to k rho cos theta, ky equals to k rho sin theta, this is Fourier domain substitution. So wherever you have kx, you substitute this. Wherever you have ky, you substitute this in different places over here, and you get f of k rho cos theta, k rho sin theta. Similarly, this over here will become, there is an x and a k rho and cos theta, and like here you all kx ky becomes k rho d k rho d theta. This is the r theta transformation from, you might remember from the 2D calculus. So basically, if you do this, you like look at this equation. This is essentially the same as f of k rho cos theta, k rho sin theta, and I've taken the k rho outside x cos theta plus y sin theta. So I'm just rearranging some terms, and so this is basically right. So there is a so fb is this equation, f of x comma y is this equation. What do you see as, what is the difference between these two equations? This one term, right? So there is d k rho d theta, d k rho d theta. All other terms are the same. The only difference between fx, fy and this is that there is this one factor in the Fourier domain, and that is the filter that you have to apply in order to get back the original data. Okay, so fx, fy can be reconstructed like after back projection. If you do this k rho time filtering, then you will get back the original object. Any questions about this? Okay, so here is a way to write this. So yeah, you can notice this similarity. So f in the Fourier domain, so this is a big equation in the spatial domain, but in the Fourier domain it's very simple. The filtered back projection data in the Fourier domain is the original object times the filter. This filter is basically this. So in kx ky domain it looks like this. In the k rho domain it looks like this. If you multiply the two, and in order, after you do the back projection, take the Fourier transform, take HE to this side, and take the inverse Fourier transform, and you get your object. Okay. So yeah, that's essentially what we need to do. This is again like sort of definition of the filter. So the estimate of your data f hat is basically h some filter times the back projected data, which FB is b times g, so back projection of the data. So D is the data, G is the data, B is the back projection transformation, H is the filtering operation. And now the data itself is the radon transform of the original object. And therefore you have this, the estimate of the data is the same as the original data, original object. The estimate of the object is the same as the original object. So therefore it means that hi times b times r has to be 1. The three operations put together are equal to 1. And so, yeah, in fact, that also means that the inverse radon transform is the filtering operator times the back projection operator. So this is called the inverse radon transform. And yeah, so the shape of the filter looks something like this. So it's just 1 over k rho, right? 1 over square root of k square plus ky square. That's the nature of the filter. You can imagine what it will look like in kx, ky, that kind of space. So if you look at it along the k axis, it looks basically like a line this way. If you look at it along the kx, ky plane, it looks something like this. So there are two basic approaches to doing the inversion. So one is, so if you think of the measurement process as start with the object, do a bunch of projections, get the radon transform data. Then how do you get back the original object? So one is first do the back projection and then do the inverse. And that way you can get the reconstructed object. That's one approach. Another approach is first do the inverse filtering and then do the back projection. Okay, so that's the second approach. Either way, you can do like you will get the same. Sorry, you will get the correct answer. Okay, so there are some subtle differences between the two. In one case, you take the data. It's a one-dimensional, like for every given theta, it's a one-dimensional data. So you apply a one-dimensional filter Hi, and that is the shape of the filter looks something. Okay, so because for every kind of as a function of s, like you take the Fourier transform along the s axis, then you do the inversion of every one-dimensional data, and then you do the back projection. In this case, first you do the back projection, you will get to the two-dimensional data, and then you do the two-dimensional filtering. So hi of kx, ky. So it will be filtering along this kind of a shape, right? So it's a two-dimensional filter. You apply a two-dimensional filter, and then after you do the inverse, you get back your reconstructed object. Okay, so these are two essential ways of doing the inverse. Both are there are good things and bad things about each, and people use different approaches to do this. Okay. So to give you a sense of what the data, like this is synthetic data, like simulations, where so the next question is, how many angles in practice do you need to get a good reconstruction? If you have like intuitively you may guess that if you have a lot of angle measurements, then you will get good reconstruction. If you use not many angle reconstructions, you will not get as good of a reconstruction, and that's actually what the simulation shows. If this is the original object, then if you take say 180 different projections, 180 different angles, and do an inverse, it looks almost exactly the same as the original. So small differences, small errors, but almost a very good reconstruction. If you just take 20 projections over here, so then it's like you can still get, like you can see there are more artifacts. For example, you can see over here, like there are these lines here, which are like there are a lot of these artifacts which come about if you do that. If you just yeah, and like yeah, if you do, sorry, sorry, yeah, if you also, so this goes from 0 to 180 179 degrees, but if you do only 0 to 90 degrees, then you're not covering the full range of angles. What happens if you, even if you make a lot of measurements, if you are not making it at all different angles, if you leave out some angles, in this case you're leaving out, you're only collecting 90, like half, like instead of 0 to 180 you're doing 0 to 90 and removing the other half of the data. You are still making 180 measurements, 180 angles of measurements, but still the range of angles is limited. In this case, you will kind of get artifacts. You can see this is very poor reconstruction. This is reasonable, but still that kind of there. It doesn't look like the original object. Okay, so this is the reconstruction quality deteriorates if there are missing angles, and this is a common problem, which is so for practical reasons, sometimes you may not be able to get all the angles, and this is especially true in optics, where if you're sending light from one direction, say you have a lens and you're focusing light onto it, so you have a range of angles at which light is falling on the object, but you cannot have light coming in this angle and this angle. So there is a certain range of angles where you get the data from, but some of the other angles are missing because the lens is not infinite in size. It has a finite size. The range of angles is limited. So whenever you have a limited range of angles, then you will have some artifacts in the reconstruction. So like how to do, we'll figure out, like um, next time we'll figure out how to kind of, what's called the best possible estimate for most kind of given the data, what is the best possible reconstruction which minimizes the error. So there are ways of figuring that out, that in a different, at a different time. But the limited range of angles is one thing that could deteriorate your reconstruction. The other thing is noise, right? So if you have even if you have all different angles, the presence of noise itself will make your reconstruction worse. Okay, so if you, so in this, in like when you add more and more noise, like even if you have full range of angles, the actual reconstruction would get worse in like a lot worse than the. So one of the things it does is it basically instead of having sharp edges, you will have kind of edges where, like, or not just edges, but all over the place there'll be some and then there'll be noise added to the reconstructed image. So this is actually, in fact, like this whatever the ray tomography that I mentioned is actually how what's called X-ray CT works, and in fact, like can get. So this is, like, these are the different sections you can measure. Like you can do a 3D reconstruction and kind of the entire, say for a head, you can figure out the shape of the skull or shape of the head or whatever. There are different object properties you can measure. You can get a three-dimensional, like for a living person, you can get the three-dimensional reconstruction of the inside of the skull, like the inside of the head, the skull and how it is, and so on. And you can even measure like the brain, like some part, like sort of the distribution of the blood vessels or some things in the brain. You can even get 3D like reconstruction. And this could be, for example, if a person has suffered a stroke, or there are a lot of different kinds of situations where something of this sort could be useful, and you can see inside the head and figure out what exactly is going on. Okay, now is a good time to pause.